We are going to be working on calculating. Oh, shooting Space Windows is going funny on me again. Oh, I'm going to be swearing in a minute. Sorry, everybody. Right. The window with your pictures is on top of my writing stuff, so I can't see my writing stuff because I'm looking at Eli staring at me right now. Not that anything wrong with you staring at me, Eli, but when you don't want you to be in the way, God, there, moved it. God, that was a pain. Okay, rates of change. The height of an object on a planet, of a rock that's been thrown on a planet, I should say, is given by this formula. If you put this into Desmos, which is a good thing to do if you want to just make your life easy, it looks like that. And we're going to be asked questions like, what's the velocity when this rock hits the ground? So we're going to find the velocity when it hits the ground. So there are a couple of things we need to do here. The first thing we need to do is, don't we need to find out what that number is? I need to know when does it hit the ground? Well, to do that, couldn't we solve this equation? When is the height 0? Now, you could simply do that by factoring, or God forbid, but you have to do it sometimes with the quadratic formula. But there is a third way to do that. And I'm setting it up right now as we speak. And that is to use Desmos. And I'm going to nip over and show you Desmos. Oh, come on, Windows. Right. Let's try this again. Right. Here is H equals the equation we just wrote down. Can you see Desmos does a really nice job of the thing? If you look really carefully, can you see that's at 2? So I know it's going to hit the ground at 2-second mark. And that is the simplest way to find that, right? If I wanted to know what the height was at the start, would you agree it's 4? If I wanted to know that guy up there, do you agree it's 0.9375? Ridiculous, ugly numbers, but at least I know where it is, right? And you can find Desmos if I wanted to know that one there, for instance. There. Yes? No?
Yes.
We're good, right? So use Desmos to make your life easy, right? Use it to find when it reaches the top, when it reaches the bottom, whatever it should be. So what we can now do is just focus on the calculus. We know when it hits the ground, it was 2-second mark. What I want to know is what the velocity is. Well, isn't the velocity the rate of change of position with time? So it's a derivative of this guy. Nothing. 30. Take away 32t. And the velocity at the 2-second mark is 30. Take away 32 times 2, 30, take away 64. And the answer I got is negative 34 meters per second. And it's correct. Why is that number negative and not positive?
Going down.
That's pretty much all it is, yeah. Would you agree at this point it's heading downwards? and downwards will be a negative velocity. If I found, you know, what it was doing at this point here, whatever this point here is, would you agree it's still going upwards, so it would be a positive velocity, right? Going uphill, positive velocity. Going downhill, negative velocity. So the slope of the tangent line, which is what a derivative is, tells you the velocity of the object. Is that not interesting connection? The slope of the tangent line is the velocity of that object. So at this point here, if I found the slope of that tangent line, that number would be the velocity. Which makes calculating velocities of moving objects very easy, because don't you just differentiate them and you put in whatever t you're interested in finding. Okay. Let's try another one. Okay, this one is h equals 2 plus 25.5 t, take away 4.9 t squared. Much uglier numbers because it's more realistic. And if I plug this into Desmos, can you just trust me? It looks like that again. You know, because it comes down. And we're being asked to find what its velocity is. And we just differentiate this, and you get 25.5, take away 9.8 t. And let's say I wanted to know at what time does this ball reach its highest, right? So what's the t value here? Well, I can use the quadratic formula, I guess, and the vertex formula and do, you know, math 141, math 99 stuff, but let's do it through calculus. What do you know about the velocity of this object right at the top of its hill? Right at the tip.
That it's 0.
It is 0. So can I just solve when is this 0? And that's when it's going to reach, right, its maximum height. And in this case, it's 9.8 t equals negative 25.5. Time for calculators to come in. If you divide both sides by negative 9.8, you have 25.5. And we'll assume that you want the answer to 1 decimal place. So it would be around about just over 2.5 seconds. So that there would be about there. Now, suppose the question then said, I like to know what the highest point is, right? How high up did that rock go? Well, I know when it happened. Won't the height just be 2 plus 25.5 times 2.6, take away 4.9, 2.6 squared? And I'm not doing that, but would you agree that would just be an answer and you would get it, right? Dot, dot, dot. Now, I have a velocity function which tells me the velocity of this object in its journey. If I wanted to find the velocity after 1, 2, or even 3 seconds, don't you just plug 1, 2, or 3 in for t and you got your answer? So if I wanted to find out the velocity at the 1 second mark, that would be my answer. If I wanted to know it at the 2 second mark, and then I could keep, I could do anything. Would you agree that once you know the velocity formula, aren't you able to get the velocity whenever, right? I could get the velocity at 2.12345 seconds for no reason except I wanted to. So far, so good. Now, suppose, same guy, I'm interested in what the velocity is when it hits the ground. That means I have to find there, which means I will have to solve when is the height 0, which becomes I have to solve this guy. There are two main ways to solve this question. You could use a quadratic formula. God, that's an ugly formula, isn't it? That would take you forever in a day. Or couldn't you just plug that into Desmos and click there and let it tell me? Now, I wonder which of those two you would choose. I would choose Desmos. I hope most of you would as well. Can you just trust me then that the answer would be at 5.28, rounded off to 2 decimal places? And that's okay because WebAssign wants the answers rounded off anyway. Are we comfortable? Do you know how you do that in Desmos? Or can I just say, you know, that's the answer and you're happy that you could do it? Or do you want to see how I would get this number in Desmos? We good? Or are we not good? You want to see it? Right, let's show it.
Just see it just for fun.
Yeah. So, kick out, go over here, open my window, make sure Eli doesn't get in my way. There we are. Okay, this here is the previous one. So all I'll do is rub this guy out. And I'll type in 2 plus 25.5 t, take away 4.9 t squared. Now, it's not uncommon that Desmos doesn't show you the whole picture. Can you see right now? Oh, we are looking at Desmos, aren't we? Okay. Can you see right now? It's just, you can't really see most of it. So if you move your mouse thing, you know, you shrink it back. There. Can you see it? Now I'm interested in there. Do you see that little guy? Can you see the 5.281? But they only wanted 5.28. That's how you would get it. If you wanted to know that number there, can you see it's 2.602? And the answer is 35.175. Now you would use calculus to find that point as well, right? Because we want you to get used to calculus. Yeah, that wasn't too hard, was it? Little side issue. Do you know sometimes when you do this thing, you get a picture? I'm trying to be really strong. You know, it looks really weird, right? Sometimes Desmos just picks a window and you think, what the heck's that shape? If it never, you know, when you zoom in, if it zooms in such a way that it's not very clear, right? This one is. There is a backup plan. Don't know if you've used it. This little tool, hit it. You can make the X values anything you like. So how about -1 to +7? Because that kind of is the numbers I want. And then I can use this guy and I can make this guy -5 and I don't know, 35. Can you see then that you have actually a lot of control over the window and the axis values? Because you know, sometimes you don't want the X's and the Y's to use the same scale, right? Sometimes you need a bigger scale this way and a wider scale that way. And Desmos isn't always good at doing that. And no matter how you shrink it and stretch it, it's hard to see what's going on. So occasionally you're going to have to go and force it by picking the X range and the Y range. And so it's just a little trick of the trade. We cool? Right. So let's return to the calculus now. Now, the question was, oops, click on this. Question was, right, when did it hit the ground? Gotcha. But they also wanted to know what its velocity would be. Now, the velocity guy at time t is 25.5, take away 9.8 t, right? And so the velocity at the 5.28 mark is going to be 25.5, take away 9.8 times that guy. And we have 25.5 subtract 9.8 times 5.28. And I get the answer negative 26.24 because they want two decimal places again. Are we comfortable with these questions that if you give me a formula for position or height, that you can find velocities at any given point? Okay. Let's move on to a different guy. Suppose the position of an object S is given by this long polynomial. And you're being asked the question, when is the velocity 15 meters per second? So we know its position, but we're not interested in what position is the 15. We're actually interested in when is the velocity 15. So to get the velocity, you differentiate and you get 4t cubed, 12t squared, take away 16t, add 15. And we're trying to find out when is that equal to 15. So that gives me 4t cubed, take away 12t squared, take away 16t equals 0, right? So far, so good. Now, I need to solve this equation. And let's do it without decimals. Let's do it as algebra. Okay, start factoring this thing for me. Any common factor you can see?
4t.
If you pull out 4t, you're left with a t squared, a negative 3t, and I believe a negative 4. Would you agree that this quadratic factors? Now, you solve. Well, this guy gives you a solution t equals 0. This guy gives you a solution t equals 4. And they're the only two that you use. Why are we not using that as a solution?
Negative.
Because it's negative. We are not allowed to do Doctor Who, those who watch Doctor Who. We are not allowed to go back in time. So it's just practical purposes, right? Now, the next question says, when is acceleration equal to 0? Well, I know the velocity function. We just found that a minute ago. To get the acceleration, you differentiate the velocity guy. And then you make it 0. And I have been pre-warned. I thought, foolish me, that this was going to factor and I'd be able to get, one or two numbers and life would be great. But this guy does not factor, which means I have two different things to do. Could I use the quadratic formula? Heck yes. Will I? Heck no. Or couldn't I just type that into Desmos and find out where it crosses the x-axis, right? So it's a totally different function. And if you take this guy, and can you trust me that it probably looks something like that, right? And you just find that guy, because you don't care about the negative number, right? You only care about the positive. And that number happens to be 2.53, because I'm telling you yes. So there is nothing wrong with you using Desmos to reduce your workload, right? To do it more efficiently. Right? So when is something zero would be a good candidate for, I'll plug it into Desmos and see what we get, right? So the acceleration is at the 2.53 mark. The significance of a zero acceleration is it's a changeover from the velocities being positive to being negative, or from being negative to being positive. Right? So there's a kind of changeover in the rate of change of those two things. So I guess you might say speeding up or slowing down might be a term you might use at that point. Yeah. There's a transition from it going speeding up to now slowing down, that kind of thing. Are we good? You happy with that question? I mean, there's a lot of duplication. What's the velocity at the 4-second mark? What's the velocity when it hits the ground, right? The usual kind of questions. Next thing we're going to do is called the average rate of change and the instantaneous rate of change. And we're not going to do it with moving objects anymore. We're going to do it with something else. We are going to look at the rate of change of a circle, or at least the area of a circle, when it's at the 2 centimeter mark. So imagine you've got a circle whose radius is 2, and you want to know the average rate of change from going from r equals 2 to r equals 3, right? So the radius is growing from 2 to 3. How will the area change in that same time slot? The average rate of change is the area at the 3-second mark, take away the area at the 2-second mark, over 3, take away 2. Can you remember in 141 the average rate of change? F of B take away F of A over B minus A. Can you remember in week 1 we also talked about the average between the two values, right? The average change in value of something. It's the same formula. Now, if you find the area when the radius is 3, you get pi times 3 squared, that's 9 pi. This is 4 pi. This is 1. And the answer is 5 pi. If you do the average rate of change from 2 to, say, 2.5, then it will be the area when the radius is 2.5, take away the area when it was 2, divided by these two guys. And when it's 2.5, you get 6.25 pi. And when it's 2, you get 4 pi over 0.5. And this guy becomes 4.5 pi. Now, if I had time, I could do a couple more. Can you imagine I did from 2 to 2.1 and then from 2 to 2.01, right? Getting closer and closer together. You could keep going until they were on top of each other. So it's a bit like the tangent line problem. And we can then make an estimate on the instantaneous velocity. What do you think these guys are homing in on? And it'd be a pretty good guess, but go for it anyway. What do you think these would get closer and closer as you moved the 2 and the other number so they're almost on top of each other? Any gut feeling for the answer?
2.
No, could be. Any other guesses? So 2 pi?
4 pi.
Yeah, let's go for 4. Well, I'd like to find out what the right answer is. Oh, wait a minute. Isn't instantaneous velocity just another name for derivative? So I'll differentiate and I'll find out what that is when r is 2. Okay, you actually guessed it right. Now, you try to imagine what the heck is going on here. Can you imagine you've got a circle whose radius is r, and then it grows by a little bit. The increase, right, the rate of change, right, how much it would move from one position to the other, is essentially a circumference worth. Would you agree that you add a bit of circumference worth of area as a circle grows? Wait a minute, isn't that what that's telling us? Isn't 2 pi r the circumference of a circle whose radius is r? So what you're getting the idea here is that as this circle increases in radius, the rate at which its area increases is by 2 pi r. It increases by about a circumference worth of area. I think that, to me, that visually kind of makes sense. You agree? Something increasing. A circumference worth of increasing. Let's look at this fella. $4,500. 1 take away 1 over 50t squared. So let's get you the story behind this. There is a tank full of a liquid. Full tank. Full to the brim. And its volume was 4,500 gallons. But there's a leak. And it's losing liquid. And this formula tells us how much liquid is going to be left in the tank after t seconds. So how much would be left, not seconds, t minutes. So how much would be left after 5 minutes? Well, plug 5 in. What volume would be left after 10 minutes? Plug 10 in. And this formula is quite realistic. Can you imagine what happens in real life? If you have a huge tank and the hole is really low down, which it would be, at the beginning, isn't the water going to be shooting out of that tank like a bullet? And then when it gets about half full, it's still going to be coming out pretty quickly, but won't it be nowhere near as fast as when it was full, right? When the leak first started. And when you're getting really towards the dregs at the end, isn't the water just trickling out? So wouldn't it be nice if we could calculate the speed, right, at which the water is shooting out, right? We would say rate at which it is shooting out. So to be able to do that, we take this fella and to find its rate of change, you differentiate it. Now, there are 2 ways to differentiate this. I don't mind which one you would do. I know which one I'm going to do. Couldn't we just FOIL this thing out, multiply it by 4,500 and get a really ugly quadratic? and then just differentiate? Or can I just leave it alone and do it as a chain rule? And that's the one I'm going to pick, but you can pick whatever one you want. So the derivative, right, 4,500 something squared. So it's going to be 4,500, right, times 2 lots of something to the power of 1 times the derivative of that something. Are you happy about the chain rule and where all these pieces are coming from, right? 4,500 something squared, 2 somethings, times the derivative of the something is the derivative of this guy. And that's where the negative 50 comes from. So I'm just going to take care of the numbers part right now. So 4,500 multiplied by a 2 and the negative 1/50th. And I get negative 180. This guy. And if I multiply this and this, I get negative 180 plus, let's see, plus 3.16. So the rate at which water is shooting out of this tank is given by this formula. So I can, for instance, tell you what the rate is when the hole appears, right? So you had a full tank and somebody got a screwdriver and banged a hole in it, right? Shooting it. At the 0 second mark, the rate at which this is streaming out of the tank is negative 180, and the units are gallons per minute. So this tank is losing fluid at the rate of 180 gallons a minute. Do you notice that the number is negative and not positive? Right, it's negative 180. What is the significance of that? Why is it negative and not positive?
Because it's losing volume.
If you're going down, right, if you're getting smaller, it's going to be a negative rate of change. If you're getting bigger, like a circle was getting bigger, right, it'd be a positive rate of change. Suppose I calculated what was happening after 10 minutes. Can you just trust me that the answer ends up being negative 144 gallons per minute? Do you notice that it's not quite as much as it was at the start, just like we predicted? Still pretty good, right? But not as good as 1A. Suppose I calculated it at the 20-second mark. And again, you're just going to trust me. It's 108 gallons per minute. Do you see? Slowly but surely, isn't the water coming out, but it's not coming out quite as quickly, right? As time goes on. And couldn't I do 30 and 40 and eventually I would get to this one. And this one happens to be 0. What's that telling me?
I can't see what's written.
Oh, that's telling you that. What is that telling us? That at 50-minute mark, the rate at which the water's coming out the tank is actually 0. I mean, it's telling us something. What is it telling us?
Here, the water line's below wherever the hole is.
Right. No more water. Empty tank. We'll assume that the hole is right on the bottom, right? Where you can't do any more. This particular formula, right? I couldn't remember with my first class. I still can't remember. Someone said it might be Bernoulli. Could well be. It's an Italian guy who came up with this formula, and it's very realistic. In other words, it's a very good model of what happens. And what it tells us is everything that we've seen experimentally, right? Or in your real life. When you stick it, if you have a hole in a tank, right, it shoots out and then it eventually disappears to nothing. And this here allows us to tell how much is in it. But what calculus now allows us to do is that we can actually predict what the speed at which you're losing your water at any given time. This would work equally well, wouldn't it, if you were talking about a boat with a hole in it? Wouldn't the only difference be the liquid be going in and not out? If it was an oil tanker and there was a hole in it, wouldn't the liquid be going out again rather than in? So when you notice that, when you talk about oil spillages, you know that the biggest amount of spillage is at the start, when there's a lot of oil and it's shooting out like a bullet. So if you don't plug up the hole quickly, you know, the horse is bolted, right? There's just going to be so much oil there that it's going to like treble your workload. So anybody who's into the, you know, the business of protecting situations like that, I'm pretty sure the first thing they are going to be thinking about is plug up the hole as quick as you can, right? First priority. I guess the second priority. First is get everybody off the boat, right? But second priority is get that hole plugged as soon as you can, because we know that this isn't constant, right? This keeps changing with time. Felt like a physics class today, didn't it? Rocks being thrown in the air, water coming out of tanks. I'm picking on physics a little bit, but I'm allowed to because mathematicians can pick on everybody because we're the only pure science. But it always kind of, I guess it's my personality. When I got a story about a hole in a tank, my first thought is, why didn't you just plug the hole up? Why are you sitting by watching it all coming out and looking at the prediction of it? Why didn't you just plug it up? And then when you do the throw a rock in the air, my thought process was, why do I want to throw a rock up in the air in Mars? I can't really think of a good reason to do that. Evidently, for fun, I guess. I mean, if you've ever thrown a rock, it gets kind of boring after a while, right? The first 2 or 3 rocks, okay, maybe interesting, but after that, it's a job. So I've never figured out why physics people do these stories, but
professional rock skipping.
Maybe professional rock skippers. Right, now, before we leave...
Fighting alien flying Martians.
What was that, Sabrina? You said
fighting
what?
Flying Martians?
Do you have many situations where you have to do that?
I haven't been to Mars yet, so I don't know.
Okay, right. Gotcha. Okay, make sure you say hi. And while that's happening, let me just reiterate, you know there's no class tomorrow. Let's be clear. But there is me tomorrow. Because on Canvas, I have a video of what tomorrow's lesson would have been. And you're going to go to that video if you haven't already done so. And you're going to answer the 5 questions that are there. And it's in an assignment, so you go in there and you've got till midnight Sunday to do it. And you'll get 2% extra credit if you get all the questions right. So I have managed to do, as I said to my other class, I have done time travel. Kind of. Tomorrow, you're going to get a lesson from me, and I'm not going to be there. Because I went into the future and I recorded my lesson and I brought it back to the present and I put it on Canvas. So you're seeing the future. You're seeing Friday when you go into Canvas. Scary. Right. But I don't think I told you any jokes in that video. So that might be a plus. Did you hear about the 2 guys talking about Switzerland? And one of them said to the other, what's so special about Switzerland anyway? And the guy thought for a minute, says, well, its flag is a big plus. Oh God, I'm getting the boom boom off Sabrina. Okay, I've made you suffer enough. Have a nice weekend, guys. I shall see you Monday. Hi, Kathy. You finished? So you got a question for me?
I do. So
Go
I
for
was
it.
looking at the 3.6 homework, and we
Yeah.
did an example of number 9 in class. But when I plugged in the answer to that into the box, it said
WebAssign, yeah.
correct.
Yeah. So what was that question? Can you tell me off the top of your head? Is it one that I have to look up, or can you read it out to me?
I'm trying to find it. I don't know how well that's working, but I think it would be faster if you tried to find it.
Okay,
'Cause
I'm got
wasn't
it.
that-
What question number was it? I'm in there right now.
It was number 9.
Okay, let's see what number 9 looks like. So if I've got it right, it's y equals the natural log. I have, in my question, I have e to the negative x plus x e to the negative x. That's the question 9 I'm looking at from section 3.6. Is that the one you're thinking about?
I don't think there were negatives in the example we did in class
They do,
or mine.
that's okay. It just means WebAssign does versions. So that was the one we did in class, right?
Yeah, so it was ln parentheses e to the x plus x e to the x.
Okay, so I'm going to go through this guy and see what might have gone wrong. I think it might just be style points. In other words, WebAssign was, the answer was right, but it wasn't written in the form it wanted. So that's my best guess. I'm going to pull out an e to the x as a common factor. And that means I can now split this into 2 logs added, which means that the, oops, too early. Isn't ln of e to the x just x? The natural log of e to the power of x is just x. Now I can differentiate. 1 plus 1 over 1 plus x. And you put that in, and WebAssign said wrong.
Yeah,
Essentially, okay. What WebAssign was looking for is that these two guys had to be combined into a single fraction. So I'm going to call 1 plus x over 1 plus x, so it matches this guy. And that means I have 1 plus x plus another 1 over 1 plus x. That means I have x plus 2 over 1 plus x. And now WebAssign should be happy.